Annenberg Media.
Good morning, Mr. Garfinkel. Where to?
It's Garfunkel, 3141 Euclid Avenue, and step on it. I'm late for my algebra show. By the way, what's the fare here?
That's going to be $2 plus 25 cents a mile.
Okay, let's see, that's 25 cents a mile. It's about 10 miles to the studio, so that's $2.50 plus the original $2. That'll be $4.50. Great, I got enough with the tip. So what do you think about the weather we've been having lately?
It should break one of these days.
Well, it's pretty clear that the further I go in this cab, the more it's going to cost me. That's because the fare increases steadily as the distance I travel increases. They're both linked together and change at a constant rate. This is an example, and I might add a pretty expensive one, of something that's called a linear relationship. When we finally do get to the studio, I'm going to go into this in more detail. In this program, we'll see that linear relationships, like the one between cab fare and distance, are represented on a graph by straight lines. We'll learn that such relations can be expressed by the general formula y equals mx plus b. We'll see that the steepness of a line is measured by its slope. Finally, we'll learn to recognize when lines are parallel or perpendicular. Well, like I said in the cab, this program is about linear relations, situations that involve adding a fixed amount over time. And with this program, we're going to begin learning how to represent situations such as increasing cab fare with pictures as well as with numbers. Now, when I say pictures, I don't mean drawing the Mona Lisa. I'm talking about graphs. In this program, and in many of the programs to come, we'll be talking about situations that involve two quantities changing. Things like cab fare and distance covered, or exam scores and the amount of time spent studying. The clearest way to represent the relation between two quantities is to use two intersecting lines or axes. By tradition, we call the horizontal line the x-axis and the vertical line the y-axis. Now we can represent any combination of values for the two variable quantities with points on our graph. For instance, the point representing an x value of 6 and a y value of 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, is here. 6, 4. Again, by tradition, we indicate points in the plane by putting the x value first, then the y value, and enclosing them in parentheses like this. This is called an ordered pair because the order in which the numbers are written is important. The ordered pair 6, 4, for instance, represents this point, where x is 6 and y is 4. The value of setting up a system like this is that we can use it to show the solution sets of equations with two variables. In the equation y equals 3x plus 5, there are many sets of y and x values that satisfy the equation. For instance, the ordered pair 2, 11 is in the solution set because if we substitute 2 for x and 11 for y, we get an identity, 11 equals 11. So the point 2, 11 is a solution to the equation y equals 3x plus 5. So are the points 1, 8, 3, 14, and negative 1, 2. If we connect these points with a straight line, we can represent all possible solutions for this equation. In this case, that set of solutions results in a straight line on our coordinate system. This is the defining characteristic of linear relations. As I said before, such relations exist when we add a fixed amount over time. The taxi fare I paid to get here this morning is one example, but there are many others.
From seeing the pictures, I'm sure I'll sleep better tonight.
With ultrasound, doctors can allay some of the fears of pregnancy. Using the fact that fetuses grow at a linear rate, doctors can take measurements of limbs and organs to gauge the health of a fetus. This thigh bone, for instance, is well within the normal range, a clear indication of a healthy pregnancy.
81 right there.
Get caught for speeding these days, and you may be in for a shock.
Your license and registration, please.
Many states have hiked their fines to discourage speed demons. The penalties usually follow a linear pattern. In Massachusetts, for instance, fines start at $50 and increase $10 for every mile an hour over 65. One of the cornerstones of astronomy is a linear relationship with truly cosmic consequences. Astronomers have discovered that all the galaxies are flying away from one another, and that the galaxies farthest away are traveling the fastest. The linear relation between galactic speed and distance implies that the stars and planets we see today originated in the Big Bang, a cosmic explosion that occurred about 15 billion years ago.
The relations we just looked at, the rate of universal expansion, speeding fines, and the growth of a fetus are all linear. They all involve adding a fixed amount over time. But linear relationships aren't limited to situations involving time. They exist whenever two quantities change in a fixed manner relative to each other. One such relationship can be found on the open seas.
Let's really get it moving. Here we go. Nice wave. Slowly bringing this one down. Guy back.
Speeding downwind in a stiff breeze is one of the thrills of sailing.
Beautiful.
With the help of honed crew, a skipper can wring every possible knot of speed from a boat.
There's a little puff. Bang gets ease. Surf down the wave. Bang back on. Beautiful.
But even the best skippers and crews can only make a boat go so fast. They face an ultimate speed limit. It's a linear relationship called hull speed.
Hull speed is the maximum speed a boat will go through the water, theoretically. And it's based on the length of the boat. The longer the boat, the faster it will go. And this is a linear function.
Creating a boat that can reach the theoretical maximum speed for its length is tricky business, however. Yacht designers like Johnstone must juggle many factors, such as weight, sail area, and hull shape in their effort to design a fast boat. Throughout the design process, Johnstone relies on algebra to help him predict the boat's chances of reaching its hull speed.
I'll start with a preliminary design and say, well, I think maybe I need this much sail area, I think I may need this much weight in the keel, etc. And then I'll plug that into my velocity prediction program, and I can come up fairly quickly with the parameters of this boat that I'm going to design that's going to be 45 feet long.
With the design finished, it's up to skilled craftsmen to transform the calculations into physical reality. Here, workers lay sheets of fiberglass in a precisely contoured hull mold. After it hardens, the hull is carefully broken free of the mold. The resulting shell is strong, light, and mirror smooth, qualities essential if the finished boat will reach its hull speed. The empty shell is filled with galleys, beds, an engine, and everything else needed to make life on board comfortable. Finally, the boat is ready for its maiden voyage.
You never really know until you put it in the water and try it out. No matter after all the mathematics and all the computer work and all the rest of it, you really have to go try it.
The first boat off the line proved that Johnstone's calculations were correct. It quickly and easily reached its hull speed of about 9 knots.
It felt sensational. As soon as we hoisted the sails, I mean, you could tell it was going to be a fast boat. When the 6 of us got off the boat, I think nobody had to say anything to anyone else. Everybody felt real good about the boat.
Now let's take a closer look at this linear relationship between a boat's length and its maximum speed. First, let's graph the situation. We'll use the x-axis to represent boat length in feet and the y-axis for maximum speed in knots, which are nautical miles per hour. Now, I can represent any combination of length and speed by finding the appropriate spot on the graph. For instance, the maximum speed of a relatively small boat, 24 feet long, is 6.7 knots, so that's this point here. The top speed of a 60-foot ocean racer, on the other hand, is 10.3 knots. The line between these two specific points summarizes the Hull speed relationship. Using it, we can get eyeball estimates of the maximum speed for any length of sailboat. But making eyeball estimates from a graph isn't very precise. Much more helpful would be an equation describing this relationship. Fortunately, any straight line, including this one, can be described by the general equation y equals mx plus b. To be useful to us, of course, we need to know the specific values for m and b that apply to our situation. Let's take m first. M is called the slope of the line. The slope m just means the steepness of the line. Large positive values of m mean steep slopes. Small positive values mean shallow slopes. And negative values mean the line slopes down from left to right. Mathematically, the slope is the rate of change between the two variables. The slope tells you how much the y variable changes for a corresponding change in the x variable. So the slope of a line is the change in y divided by the change in x, or rise over run. You can find the slope of any line as long as you know the values of 2 points on the line. For this line describing Hull speed, we know the coordinates for 2 points, 60, 10.3, and 24, 6.7. So what's the change in y? That's 10.3 minus 6.7, which is 3.6. And the change in x? That's 60 minus 24, or 36. So the slope is the change in y, 3.6, divided by the change in x, 36, which is 0.1. That means for every unit I move on the x-axis, I'll move up 1/10 of a unit on the y-axis. Again, here are the steps to find the slope of any straight line. Choose 2 points, subtract their y values, subtract their x values, and divide the difference in y by the difference in x. Now we're halfway toward finding the equation of our Hull speed relationship. We still need to find a specific value for b, the other term in the general equation y equals mx plus b. Well, b represents the y-intercept, which is exactly what it sounds like. It's the place where the line intercepts or crosses the y-axis. You can usually get an eyeball estimate of b by looking at the graph and seeing where the line crosses the y-axis. But for a precise answer, you can use algebra as long as you know the slope and at least 1 point on the line. Remember that the beauty of algebra is that you can always find an unknown value like b if you know the rest of the ingredients in an equation. In this case, we know the slope, which is 0.1, and we need a pair of values for x and y. Let's choose 24 and 6.7 and plug them into the equation. Now we have an equation with one unknown, so we just solve it using the rules of algebra. That 6.7 equals 2.4 plus b. So b is 6.7 minus 2.4, or 4.3. So the line crosses the y-axis at the point 0, 4.3. What would happen if we used the other point? Let's try it out. The slope 0.1 is the same. So the equation is 10.3 equals 0.1 times 60 plus b, or 10.3 equals 6 plus b, which means b equals 4.3 again. You can see that it doesn't matter which point we use to calculate b. Now we can go back to our general formula for a straight line and substitute the values we found for the slope m and the y-intercept b. There it is. We found the equation summarizing the relationship between a sailboat's length and its maximum possible speed. The speed is 1/10 done. We saw that any straight line can be described by the general formula y equals mx plus b, where y and x are the two variables, m is the slope, and b is the y-intercept. We learned that slope is the change in y divided by the change in x, or rise over run. Finally, we learned to find b, the y-intercept, by using the slope and the coordinates for any point on the line. This is unbelievable. Look at these guys. I asked for a couple of crickets for a demonstration, and what do I get? 500 crickets. Well, these guys are common American field crickets. You're probably more familiar with them by the sound that they make. Can we get some cricket sounds down here? There, that's better. Like I said, almost everyone's heard crickets before, but most people don't know that cricket chirps can be used as a thermometer. See, the pace of a cricket's chirping is directly related to the temperature. The hotter it is, the faster a cricket chirps. It's a classic example of a linear relationship. Since the relationship is linear, we can summarize it with a line on our graph and an equation. Y equals 1/4 times x plus 37, where y is the temperature in degrees Fahrenheit and x is the number of chirps per minute. Suppose we hear a cricket chirping away 132 times a minute. Using the equation, we can substitute 132 for x and solve for the temperature y. We find that if we hear a cricket chirping 132 times a minute, the temperature, at least in the vicinity of the cricket, is 70 degrees Fahrenheit. Okay, and what's your rate per mile? Right. Now, that's on top of the $1 base charge, right? Good. All right, well, thanks a lot. Great. I found a cab company that's cheaper than the one that I took to get here this morning. These differing cab fares illustrate a few basic points about the slopes of straight lines. I'll plot the information on a graph with distance in miles on the x-axis and total fare in dollars on the y-axis. Each company has a base charge and then a certain amount for every mile after that. Ace, the company I took to get here this morning, charges $2 to start, that's this point here, plus 25 cents per mile. That 25 cents a mile is the rate at which the fare increases, so it's the slope of the line describing this relationship. Now, how do we find a line when all we have is one point, the $2 base fare, and the slope? Well, remember, slope is rise over run. Since the slope in this case is 25 cents, that's the same as 0.25 over 1, which means I go up 25 cents for every mile I go on the x-axis. So to find another point in this line, I just go over 1 mile on the x-axis and up 25 cents on the y-axis. I mark my point, and now I can draw my line. I also called the King Cab Company. Their fares start at only $1.50, and the rate after that is 25 cents a mile, just like Ace's. So, just as before, I find the one point I know for sure, the $1.50 base charge. I go over a mile and up 25 cents and draw my line. Well, it's obvious which of these is the better deal. No matter how long the trip, I'll always pay less with King. That makes intuitive sense, but it's also clear geometrically because these lines are parallel. You could extend them forever and they'd never meet. And that illustrates an important point about slopes. You probably noticed that these two lines have identical slopes, 25 cents a mile. This is a specific example of a general rule. Lines with equal slopes are parallel. On the other hand, if the slopes of two lines aren't the same, you know that they cross somewhere. There's also a third company in town, Jack's Taxi. It charges a base fee of only $1, which is great, but the rate is 50 cents a mile after that. Again, I can draw the cost line using the y-intercept, $1, and the slope, which in this case is 50 cents a mile. Look at that. The total fare with Jack's is lower than the other two for the first 2 miles, lower than Ace for the first 4 miles, and higher than either after that. Jack's Taxi goes from being the best deal in town to the worst. That's clear from the graph, because the line for Jack's crosses both the other lines. Now, what does it mean when two lines cross? Well, the intersection point is common to both lines, which in turn means that the pair of xy values on a graph is common to the equations that describe both lines. Now, just for fun, imagine another taxi company that charged a base price of $3, but no mileage charge after that. What would the graph of that relationship look like? As before, we know one point, the initial rate. But since there's no charge after that, the total fare remains the same no matter how far you travel, and the line, therefore, is flat. What's the slope of such a line? Clearly, there's no rise, so the slope must be 0. And since the slope is 0, and 0 times any x value is 0, the equation for this line is just y equals 3. And that means that the fare y is always $3 no matter how far you go. Okay, so what about a line like this? The equation of this line is x equals 4. What in the world would this mean? It would mean that if you called this cab company, you'd absolutely have to travel 4 miles, no more and no less. And the fare, that's y, could be anything at all, from nothing to $100 billion or more. That would be one weird cab company. Can we say what the slope of this line is? Not really. Since y can take any value, we say that the slope of a vertical line is undefined. Okay, let's bring back for a minute the line for ACE. Now, what would you make of a line like this? This line is perpendicular to the ACE taxi line. That is, it intersects the line at a 90-degree angle. Now, this is my kind of cab company. Look, the fare starts out at $6, but the fare decreases the further I go. Let's figure out the slope of this line. For our 2 points, let's use the y-intercept, 0, 6, and this point here, which is 0.54. So the rise in this case is 2. The run is 0 minus 0.5, which is negative 0.5. 2 divided by negative 0.5 is negative 4. So the slope of a line perpendicular to the line for ACE is negative 4. The important thing to notice here is the relationship between the slope of this line, negative 4, and the slope of the line that it's perpendicular to, which is 0.25 or 1/4. If you multiply 1/4 by negative 4, you get negative 1. That means that 1/4 is the negative reciprocal of negative 4. The slopes of perpendicular lines are always negative reciprocals of each other. You can always find a negative reciprocal by treating the number as a fraction, inverting the numerator and denominator, and reversing the sign. Here's a pop quiz to test yourself. The negative reciprocal of 2 is negative 1/2. The negative reciprocal of 3/4 is negative 4/3. The negative reciprocal of negative 1 is 1. The negative reciprocal of negative 12 over 27 is 27 over 12. So if you know the slope of this line is 5, and the slope of this line is negative 1/5, what can you say about the lines? The lines are perpendicular. Let's see, swimming pool, beaches, palm trees. Sounds great. This coming July, I'm going to give a math lecture in Canada, and then I'm going to Hawaii to relax. But the tourist brochures I've gotten say that the average temperature at that time is 86 degrees in Honolulu and 30 degrees in Calgary. Does that mean that I've got to lug my parka along with my swim trunks? I'm not sure, because the temperature in Hawaii is in Fahrenheit, and the temperature in Calgary is in Celsius. If I could convert one to the other, I'd be all set. Now, there's a nice linear relation between these two temperature scales. I don't remember the formula, but I do remember 2 things: the freezing point and the boiling point of water in both scales. That's all I need to figure out how to pack. The key is finding the equation that relates the 2 temperature scales. First, let's draw a picture. We'll call the x-axis temperature in Celsius and the y-axis temperature in Fahrenheit. Now, our 2 points are the freezing point, that's 0 Celsius and 32 Fahrenheit, and the boiling point, 100 Celsius and 212 Fahrenheit. So here's the line. Now what's the slope? Remember that slope is rise over run, the change in y divided by the change in x. Since we called y Fahrenheit and x Celsius, that's 212 minus 32 over 100 minus 0. So the slope is 9/5. Okay, with the slope in hand, let's find b, the y-intercept. Since our first point is 0, 32, we automatically know the y-intercept. It's 32. With the slope and the intercept, we now know the formula for the Fahrenheit-Celsius relationship. It's y equals 9/5 times x plus 32. But let's use the more familiar symbols, F for Fahrenheit and C for Celsius. We're almost finished. Since we're told that the average temperature in Calgary in July is 30 degrees Celsius, we can use this formula to convert that temperature into Fahrenheit. We replace C in the equation with 30 and solve for F. So that's F equals 9/5 times 30 plus 32, which is 86. Aha! How about that? 30 degrees Celsius is the same as 86 degrees Fahrenheit, which means that I can leave my parka in the closet. Well, now we've met a number of linear relations, and we've seen how helpful it is to graph such relations with a coordinate system. One skill that's particularly helpful in working with graphs is determining the distance between 2 points. We can find the length of any line segment by using the coordinates of the endpoints and that old standby, the Pythagorean theorem. Let's say we know 2 points on a line, -4, 3 and 8, -2. What's the distance of the straight line connecting them? To figure this out, we make a right triangle. The length of the horizontal side of the triangle is the difference between the x values for the 2 points. Here, that's 8 minus -4, which is 12. We find the length of the vertical side the same way. That's 3 minus -2, which is 5. With the Pythagorean theorem, we can now calculate the length of the hypotenuse, which will be the length of our line segment. So, the distance between our 2 points is 13. We can create a general formula for finding the distance between any 2 points by using the same logic with the ordered pairs x1, y1, which we'll call point P, and x2, y2, which we'll call point R. If we use the Pythagorean theorem, we find that the distance between P and R squared is x2 minus x1 squared plus y2 minus y1 squared, which leads to the distance from P to R is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Now we've learned all of the basics of linear relationships. We've learned how to find the slope of a line, as well as how to determine the distance between any 2 points on a line. We've seen how to find the equation of a line if we know 2 points, and we work the other way around, drawing the line describing an equation if we know the slope in a single point or just 2 points. In the next program, we'll continue to use graphs to represent algebraic expressions, except this time we'll work with curves that describe changing rates over time. Such curves are typical of many real-life situations, such as population growth. Which reminds me, what the heck am I going to do with 500 breeding crickets?
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.